Hi, my name is Morgan Berkeley. I am presenting my KI5 video presentation right now. I am currently taking all three of the 300 level junior level classes, so 342, 312, and 332. So right now I'm going to start with question 1 of the KI5, which is this beautiful radio system diagram. So basically, we start with the antenna, which receives or transmits a signal, which right now we're just going to deal with the receiving end. So we receive our signal, goes to the diplex, and basically this tells us whether or not we're on it or not. And then we have a bandpass filter, which looks like this. And then it goes through an amplifier, which amplifies our signal. And then we have our mixer, which we have our carrier frequency, or like just another signal that we mix it with. Probably like a sine wave or cosine wave, which actually like decreases our amplitude to half of what it is, but we have two of the same like signals now, or frequencies now. So we amplified this again just so we can get that like half the amplitude or half of the magnitude up to what it originally was before the mixer. And then we have this lovely low pass filter to help filter out some of those other unwanted frequencies that this original band pass filter didn't get. And then also it filters out one of those frequencies that was added to by our mixer. So that's that. So next I am going to answer the one second. So I'm going to actually skip question 2 just because I feel like it's not that important and I don't think I'm going to have enough time to answer it. So I'm going to skip straight to question 3. So for this one, we are asked to like basically like derive the transfer function for a simple LC oscillator and draw its pole location. So for this, I just did a bunch of math for it, I guess. I don't really want to go into it that much, but I ended up getting my transfer function as a equals a equals there we go, a over 1 plus a f for the transfer function for that one, and then for the poles I ended up getting for this one I ended up getting s is equal to plus or minus j over the square root of LC. That is what I got for those two bad boys. So we have a little bit of a discussion about where the pole locations would be, that I assumed it would be purely on the imaginary axis and not on the real axis because we only have this j component. So I just assumed it would go up and down this imaginary axis. It would either be down here or be up here in the imaginary axis. And then what circuit technique can you provide to tackle the impact of a parasitic resistance in the LC loop? So we basically just did a simple block diagram, which would just give us like an L and an R and then a C, and that would be basically the entire thing. So for number 4, we were asked to basically solve for this circuit. We have to find the words. We find the closed loop transfer function for this circuit for both ideal and non-ideal. So for the ideal transfer function, I think everybody got that it was minus ZF over ZI, and that was it. It's pretty simple. And then for the non-ideal, we did basically what it just says, that you multiply it by this. So it's just ZF over ZI times A over 1 plus ST. So it's pretty straightforward in my opinion. So for 5, we basically just like put these into what it says, and then, not into what it says, but like this, into the specific things that you're supposed to put it into, and you get the transfer function for those things, which is pretty long, but, I mean, I'm sure we all got similar things, and I will show you what the MATLAB images look like if I can pull them up real quick. There we go. Alright. So for the MATLAB images, this is what we got for the first one, which was the closed loop, the closed loop gain for the ideal circuit, which is just the R and the C and R circuit. It's a pretty simple 3D diagram. And then this is what we got when it was the non-ideal. You kind of just get like an extra bump, which makes sense because we basically added an order to our transfer function. So it gives us that extra like bump in the magnitude diagram. It gives us these like kind of ripples as opposed to what we have in this. And then for question 6, we are asked to do basically the same thing, but we have an extra capacitor out front. So for that one, it basically just ends up being a bandpass filter. Woo. And then this is for the ideal circuit, and then here's for our non-ideal circuit. They like kind of elongate it, I guess, what happens. So that's pretty much all for that bit of it. So now for number 7, we are asked to talk a bit about this silicon lab board thing, which is just basically in the schematic, different parts of the circuit can be distinguished, blah, 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 blah. So what are the function of the matching network? For this one, I said, hold on 1 minute. For this one, I said that the max power transfer can be, for the max power transfer and the reduced reflection line, and then assume that the PCB material is low, type of material is this, blah, 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 blah. The circuit operates at this. Do the dimensions of the antenna and transmission line confirmed through the wavelength? And I said yes, and there was some math behind that, which is over somewhere else. So yeah, and then impedances. So for this one, I chose 75. So again, some math would be Z O equals the thing that looks like an N, I think it's mu naught, and then over square root of epsilon R times, I guess, mu naught equals mu naught over the square root of epsilon R times lambda over mu. I can't really read my own handwriting right now. Lambda over R, because So this part right here. I honestly can't remember what I was doing when I did this. Yeah, which this is closest to 75. So, yeah. And then for this part, the arrows in figure 5 indicate the direction of maximum radiation power based on the material. Can you justify the pattern with physical concepts? So, for the coax cable, oh, sorry, okay. Basically it's just standard antenna with dipole antenna having max radiation when normal. So it's just basically just like a simple like antenna layout. And that's basically all. I think I went a little bit over. I'm sorry about that, guys. Bye. Have a great rest of your day watching videos.